on to the next speaker, Florian. Yes. Yeah, Paolo.
Hello everyone, do you all hear me?
If you can stop screen sharing, Paolo.
Okay, thank you.
Thank you. Thank you very much.
Hello everyone, do you all hear me?
Yes.
Oh, okay, thank you. Okay. Do you all see the screen of my presentation?
Yes.
Okay, thank you.
So we're 5 minutes ahead of schedule, but I think we'll just start, I think, please, Florian, go ahead.
Okay, sure. So first of all, I would like to thank the organizers for letting me present part of the results I've obtained during my 3 year of thesis. So what I'm going to talk about today, the maps of phenomena for breaking waves in deep, intermediate, and shallow waters. More precisely, I will talk about the investigation that I've made while creating these 3 maps. So, first of all, what is a map of phenomena? For me, a map of phenomena is a way to predict the breaking event thanks to the initial characteristics. So it can be the wavelength, it can be the wave steepness, the bond number, etc. So when I started my thesis, I have found these 2 papers, these 2 map of phenomena that exist in the literature. So the first one in the left, which was created by Luc Dijker in 2015. So it is the most recent one and the most complete one. And it's representing the different type of breaking thanks to the slope and the bond number, but it only focused on the deep water. On the contrary, the second map of phenomena, which was created by Pierre Lubin, my thesis director, only focused on the wavelengths, but there is a variation of the water depths. So I've decided to kind of mix them together and create 3 different maps of phenomena with a modification of the slope, of the wavelengths, but also of the water depths. In order to do so, I've used the code Notus CFD, which is developed inside my team, and it's solving Navier-Stokes equation with the gravity, viscosity, and surface tension, and it's representing multi-phase flow. And I've taken for properties the air and the water at 20 degrees. My initial condition was first order Stokes wave in a periodic domain over a flat bottom. And all of the results I'm going to show you today are only based on 2D simulations. And a particular thing of my research is it is based on small wave, which is from 5 centimeters to 35 centimeters. So there is a huge impact of the gravity and also the surface tension on the breaking event. And in order to create these 3 maps of phenomena, I've performed more than 180 simulations. So this is a representation of the wave characteristics I've taken with lambda the wavelength, A the amplitude, and D the wave depth. And this is the relationship that we can calculate thanks to these characteristics. So the wave steepness, the water depth. And today I'm gonna talk about these 3 wave numbers. I'm gonna use these 3 wave numbers, which are the wavelengths, lambda, the wave steepness, epsilon, and the water depth, which is a ratio between the wave depth D and the wavelengths. And one thing that you should know is that all of the results that I'm gonna present are coming from a wave which is moving from the left to the right. Before presenting my investigation and the different maps I've obtained, I just wanted to briefly present the different type of breaking waves that we can observe during this for this kind of wavelengths, so for the small wavelengths. The first one, breaking type, is the parasitic capillary wave, PCW, which represents a small train of capillaries created during the wave movement. And it's kind of an illusion because all all capillaries are moving with the same celerity as the initial wave, which creating kind of all moving together wave train. This phenomena comes from mainly at the surface tension, so it's only related to a small wave, small breaking wave. The second one, which is a spilling breaker with high surface tension, this is really important because this is not the same phenomena as the spilling breaker which were presented today. So it's kind of different, and the phenomena are only related to the surface tension. So it's also only for small wave. And the breaking process created a massive movement of the surface, just like here. And if we go further in time, the movement of the surface will become much more massive. And the last one, which is the most common one, and there is a lot of talk about it today, which is the plunging breaker. So there is a generation of a jet here, which will impact the surface, and it will capture a roller here. And during creating my maps of phenomena, I try to understand what's happening during the breaking process. And I found 3 new subcategories of the spilling breaker, the general spilling breaker that are on the literature. The first one are related to the spilling breaker, and I will talk about a spilling breaker with single vortex and a spilling breaker with dipole. The last ones I've observed is the plunging breaker, but without primary roller. In order to present the spilling breaker, I needed one new breaking criterion, which is the capillary angle. So I'm going to talk about it now. On the literature, they decided to characterize the breaking of parasitic capillary and spilling breaker thanks to the capillaries generated. So they are trying to characterize the celerity, the wave stiffness, the length of the capillaries, the slope of the front and the back. But one thing that I never tried to understand is this angle. What we can see, first of all, there is kind of a difference between the angle on the left and on the right. The angle on the right is lower than the angle on the left. In fact, there is interesting value here, which is the minimum value of this angle. I have plotted the evolution of this angle through time during a breaking process, which is here a parasitic capillary wave. So first of all, the angle reduces just like is compressed, and after a while, after reaching a minimum value, it starts to increase again, just like a decompression. And what is really interesting is the minimum value. In fact, I have plotted all of the results of the minimum value that I have obtained on every water depth for the parasitic capillary wave represented by a blue square and the spilling breaker represented by a red cross. And one thing that is showing that there is 2 different regions. It's kind of, there is a limit angle, which is approximately 90 degrees, which represents the difference between both breaking waves. Now I'm going to present you the different subcategories I have found. So the first one is a spilling breaker with single vortex. I'm going to present you first of all a video of my simulation. So the black line represents the interface between the air and the water, and the colors that are going to appear on the video is the vorticity. So the wave will start to break, creating here a vortex. So there is a vortex here which is generated, and it's kind of a single vortex. So every time that I'm going to show a video, I'm going to after show some pictures at different time for this breaking. The first point is the capillary angle located on the second picture is under 90 degrees. So every time that the angle is under 90 degrees, it will release, just like here, a vortex and a small wave going backwards. So on my simulation here that I'm presenting today, there's only one single vortex, but there can be 2, 3, 4 are obtained and obtain 4 single vortex. So this angle can go above 90 degrees and releasing a vortex, and then going below 90 degrees, releasing a second vortex, etc. So there can be multiple vortex, but there is one thing that I wanted to put on my title is this is a single vortex. What I'm meaning about it? So I'm meaning that there is no interaction between the different vortex generated. So it's kind of this vortex doesn't seems to be how can I say it? There is no interaction, there is no influence of this vortex to the next one and again the next one. So they're kind of single. And also, one thing that I've observed is that for every single vortex that obtained, there is one just above the surface in the air. So it's located at the same position and it's moving exactly the same way as the one underwater. So just like I've explained before, we can see it here by a small wave generated going backwards. And it's really important. And one thing that I've observed is that in the literature, this kind of breaking is put under the labeling of a general spilling breaker. And one thing that will be really important for the end is that the vortex generated here have a horizontal velocity which is really small in comparison to the wave velocity, the wave celerity. So it means that this vortex will stay in the same place in the same area of its creation. Now, if I'm presenting the spilling breaker with dipole, so again, the wave will start to break, and there's the first one vortex generated, a second one, and there will be an interaction between the vortex modifying the surface motion. And as you can see, there is a first dipole here, and there is a second one which is created at the end of the simulation. So here, so I've put an arrow of near the angle, the capillary angle, so we can follow here easily. And every time the angle is under 90 degrees, it will create here a vortex. So the first one, the second one, there's a third one, fourth one, etc. So there are many vortex generated. And one thing is, if the multiple vortex generated are so close to each other, they will start to interact and they move, they rotate around each other, modifying the surface motion and creating this kind of profile of the surface. So here on this surface, there is a high curvature. So the surface tension will create a movement towards that direction. And also it will release here a dipole of negative vorticity and positive vorticity. So this interaction is really important because at every time there is an interaction, there is a dipole generated. So here's the dipole ejected, and the dynamic of this dipole is going towards the bathymetry. So it's going downwards. Sometimes randomly during this process, a bubble can be captured, but I've never find out why sometimes there is a bubble and sometimes there isn't. So there might be a bubble during this process. And again, even though that this last spilling breaker with a single vortex this behavior is different, they were put on the same labeling, which is a spilling breaker. So they're totally different. They're not exactly the same behavior. And again, there is something which is really important, that the vortex horizontal velocity of the vortex generated here is small in comparison to the wave celerity. So again, the vortex will stay in their creation area. Now, if I present the last one, which is the plunging breaker without primary roller. So the wave will start to break, but there is here the surface tension force which will act and the jet won't be able to connect with the surface. We can see there is a splash up here created on the secondary roller. And in the meantime here, there is a vortex, a huge vortex, which is generated at the location of where the primary roller should be. So for this numerical simulation, I found no roller generated, and it is due to the curvature here, which is really high. So the surface tension will create a motion towards that direction, so the jet won't be able to connect with the surface, so there is no roller generated. But one thing is that there is a big vortex which is generated by the movement, the inertial movement of the falling jet. So this big vortex is exactly located at the position, at the place where the roller should be. And what we can see, which is different than the previous simulation, is that there is a splash up generated, and also there is secondary roller, which is captured here. And I don't put it until the end, but there is a third roller, which is captured also. So during my reading, I tried to find this kind of breaking dynamics. I found only two papers who are working on it in my knowledge, but they were put on the spilling breaker level. But in my opinion, the behavior, the dynamic process is much more closer to the plunging breaker than to the spilling breaker. In fact, there is something which is really important that I've talked about it before, which is the horizontal velocity of the vortex generated. In contrary of the spilling breaker, all of the vortex generated here, the big one, and the vortex inside the splash up, they will be transported by the braking dynamics, just like the plunging breaker with primary roller. So this vortex won't stay in the local area of the generation, but they will be transported to another area. So for me, this is much more closer to a plunging breaker than to a spilling breaker. So this is why I've decided, so in my opinion, it's just much more plunging breaker than a spilling breaker. Now I've presented the different subcategories of breaking waves that I found during my investigation. I'm going to just present briefly the maps of phenomena that I was able to recreate following in the wave steepness in the y-axis and the wavelengths in the x-axis. So here on the graph, every symbol that you can see is a simulation that I've performed to have information about the breaking type and what phenomena that we are able to see. What you can see also here is the limit in the curve. So this limit was created by studying the capillary angle, so the breaking criterion that I've shown before. So I've taken all of the minimum value of the parasitic capillary waves breaking and the spilling breaker. I have reconstructed a function in order to predict the value of the minimum value of the capillary angle, and I have for result this kind of curve if I put it at 90 degrees, which is the separation between both breaking type. So this is what I have obtained. And one thing that you can see is that even if I have added subcategories breaking type, the region of the breaking process are not overlapping. So there is kind of a difference, and there is a particular area of a slope and of the wavelength that each breaking type are occurring. And finally, I was able to reconstruct 3 different maps. So the first one, which is for shallow waters, the second one with intermediate water, and the last one, which is for deep water. I started with the deep water one, and I have validated the results with the literature, and my maps is in a really good agreement with the maps made by Luc Dijker on deep water. So this is why I've decided to do exactly the same exercise on intermediate wave intermediate water, sorry, and shallow water. So this is what I've obtained at the end of my thesis. So to conclude, I have done many numerical simulations in order to investigate the breaking event for very small wave for 5 centimeters to 35 centimeters. And I was able to redefine a new breaking criterion, which is the capillary angle, which helped me to understand the breaking process of the spilling breaker with single vortex, with dipole. And I have found another one, which first of all was put under the labeling of spilling breaker, but in my opinion, is more suited for the spilling breaker labeling, but it is without primary roller. And I've created 3 maps of phenomena for shallow water and intermediate water, which are kind of original. And I have validated my results on deep water maps of phenomena that already existed in the literature. And for my future work, I'm trying to do 3D simulation in order to understand if the phenomena that I was able to observe are related to 2D simulation or they are also 3D simulation. So I'm trying to understand, okay, if that's not 2D artifact. And finally, I'm trying, but I'm a bit struggling with it and I'm working on it to do some comparison of the subcategories I've observed and with the experimental results that are on the literature for now. So thank you for listening to my presentation. I want to leave you with this with sentence said by Mark Berkeley in the B Waves 2018, which is breaking wave is when it becomes interesting. So thank you all, and if you have any remarks or questions, I'll be happy to hear them.
Yeah, thank you very much for the nice presentation, Florian. Very interesting. Are there any questions? Okay, so I have a question actually. So the question is so I think it's very interesting. You see the capillarity almost acts like in some sense like a foil, right? That almost like a solid boundary actually, which so I was just wondering, is this known whether so is the free surface breached when you get this creation of vorticity, or is that before or after the free surface is, like I'm talking about like air entrainment,
I'm really sorry, can you define breach?
Well, no, I don't know how to define it. Let's say we define it by, so breaching means you have air entrainment.
Okay. So I'm gonna go to so this one. So for the capillary angle, for all of my simulation, I didn't find air entrainment at this moment. So there's no air entrainment in my simulation. I don't know for the experimental and for the 3D simulation, but on my 2D simulation, there is no air entrainment on this particular capillary angle. I don't know if I'm answering well your question.
Yes, absolutely. Yeah. And so what, but what about the others? So that's the 90-degree angle. What about the others though?
The others here?
Yeah.
Most of them are above 90 degrees, so there is no releasing of vorticity. So that's what I found. But so this is only this one. I'm going to try to put the arrows. So this is only this one, which is the main thing which is acting on the breaking dynamic. I'm trying to understand the frequency of the releasing of the vorticity to be able to improve the understanding of this breaking process, but it's really, really difficult for me.
So actually, I don't know, Matteo, are you still here? I wanted to ask whether you know, in the experiments you showed that also their capillarity maybe was important, because, you know, that like on your last slide, it was rather a thin layer there, right?
Yeah, I think so. Yes, there is some. There were some disturbances at the gauge where we have recorded the breaking effect. So there is some roughness there. So can be there. Yeah, absolutely.
Yeah. Yeah, I think that's very interesting. I mean, those pictures are really, really nice, you know. Yes. Okay, so there's a question here. I will read it. This is from Syed Ahmed Hassan. When vortices are transported, is there a current-like situation beneath the free surface?
Can you repeat, please, if it's
Yes.
possible?
So when the vortices are transported basically away from the wave, so can you interpret this like a current beneath a free surface?
Yeah, exactly. Yeah, there is an acceleration of the velocity near the surface, so there is a current just beneath the free surface.
I see.
And it also induces an acceleration of the energy dissipation rate.
So I'm just going to ask another few questions, unless somebody else has any questions. But I mean, so so how do you expect a 3D experiments to be different from those here?
For the spinning breaker, in fact, I've already done some 3D simulation. So for the spinning breaker, it's really good. It's kind of the same dynamic than the 2D one, but I've not done it on the plunging breaker, so I don't know for this one. But for the spinning breaker, it's kind of the same. So as I don't presented it today, so I just wanted to be sure that I'm only doing 2D for now. But it's kind of the same behavior for 3D on the spinning breaker.
Okay, one other question that I have is, so okay, so sorry, but I just it seems very interesting. But so I mean, if you actually go to the ocean, right? So I wonder. So in the lab, it's clear capillarity can have a large impact. What about the ocean? I mean, you have foam. There are a lot of things on the free surface, right? So, do you have thought about that?
I'm not really sure because, of course, there is fluctuations. There is some modification of the surface. I'm pretty sure there might be a modification of the capillary angle, so there might be a modification of the vortex release. And of course, if the vortex is different, so there might be not the same behavior. More precisely for the kind of not strong vorticity, because there are some of them that they are much more intense. So there might be a difference on this behavior. I'm not really sure there might be a difference on the whole behavior of the breaking process, but just on small things. But I don't know, it's just my thought, and might be different. So I've never done experimental, so I don't know.
Okay, so I don't know if any anybody else in the audience has any thoughts on the role of capillarity in real ocean waves. But
I have one
yes,
general question. Very nice presentation. Thank you so much. So all of these simulations, you have sort of undisturbed flow field at the beginning, right?
Yeah.
So you basically don't have any background turbulence. So it's like turbulence free field. Do you have any idea about if you have some existing, TK patches, and then you get your wave interact with that? Would you expect any kind of deviate from the results you got?
I'm not really sure about it. I believe that might be really different on the behavior, because if there is already a turbulence or maybe a vortex underwater, so as we can see, there is a huge influence of the interaction of the vortex on the motion of the surface. So there might be real difference if it's not on a kind of perfect simulation with no wind, with no current at first. So I think, yeah, there might be a difference if there is turbulence at first.
Right. Yeah. Can you, in your simulations, can you have some like, can you send another wave? When you have like one event, can you look at the second event and see how it differs from the previous one?
Actually, I
Are
can
you able to look at this numerically?
This is a point that I wanted to do on my thesis, but it's taken too much time. I can do it on the periodic Stokes wave, but I can do it actually on if I initialize a solitary wave, I can initialize two solitary waves, one in front of each other, and just to see if there is an influence. But I've never done it.
Mm-hmm. All right. I have one more thought if nobody else. Okay. There's another question. So
just continue. We'll take that after you're done.
Okay. So regarding the 2D and 3D simulations, I would expect, as you said, if you do the 3D simulation at the very beginning of the process, I would expect the same kind of result. But immediately after you generate turbulence and vorticity, it's going to be 3D. So the evolution of the vorticity field. So there are some nice experiments by Duncan. So you can see that all the vorticity is going to be 3D. So the evolution of the vorticity and dipoles you show, I think if you do the 3D simulation, is going to be much different. So just as a comment.
Yeah, the simulation that I've performed here are until the second period, so just the first stage of the breaking process. I don't really know about the late stage of the breaking process. There might be a huge difference. Yeah, that's true.
Thank you so much again.
Thank you.
Yeah. Okay. Great. Syed Ahmed, you raised your hand. Hello.
Yeah. Hello.
Hi.
Yeah. So actually, my question is not with Florian. It's the question with Professor Murtaza. And actually, I want it's better to have asked this question to Professor Banner in his first talk. But this thing is related. It is related to the kind of question he asked to Florian. So suppose it is, it is very not very convincing for me that in case of say you have a U by C type of parameter that characterizes the onset of breaking, and it is very indifferent to initial conditions, as Professor Murtaza was saying, that you have a background turbulence, or suppose you have a two-wave breaking events in just conjunction, as one happens just after the other. So still that 0.85 U by C is valid in that case?
I'm really sorry. I couldn't able to understand your question.
So, I mean, the question was basically if you have two breaking events very close to each other, as far as I understand.
Yeah. So basically you will have a, say, you do not, in general in engineering, and rather than the quantum mechanics where you have an ontological problem that events are actually probabilistic in nature. So in case of engineering, we are generally do not have full knowledge about the initial conditions or other stuff, and that induces some probabilistic, say, statistical distributions also. Okay, so but what actually my question is towards Professor Murtaza. So in the onset of wave breaking, that parameter 0.85, which is the U by C parameter that Professor Banner was talking about yesterday in his first talk. So that seems to be very stable. It just does not change. Say if you have say background turbulence or say sort of a two-way breaking events having in conjunction. So can this change? That is because most of the experiments are done with only one way breaking events and some this calm water conditions. So suppose this was different, but as he had shown in that he had mixed the vorticity or the shear flow with the wave, it did not change. So that is kind of surprising to me. So I just wanted some thoughts about that. So I think this question was aimed at Dr. Professor Murtaza. So if he could ask one.
You want to answer? Okay.
Not really. I'm gonna look on
No,
it.
sorry, this is a question for Murtaza Derak.
Is it a question for me?
Yes.
Oh, okay. Yeah, we've done, well, I'm not sure if it's good to, but yeah, we've done some cases with multiple breaking, and as long as you do some sort of a smoothing, because when you have rough surface, defining the crest speed is, you always need to do some sort of smoothing and to have a robust estimation of things. But yeah, surprisingly, even in case of multiple breaking, you would see that kind of behavior.
Okay, good. So the parameter B is stable even if you have maybe several breaking events close to each other.
Yeah. So the recent JGR paper, you can see some of the result there. So.
Okay, great.